So why estimate systems engineering effort? So we know that there are many factors that can go into the overall cost of a project, and the technical management and systems engineering is usually a very significant one. Research has shown that adequately staffing systems engineering effort at the beginning of a project lowers the likelihood of cost overruns experienced later on in the project. So what we have here is a graph from a study done by Eric Honor on NASA data in 2004. And as we can see, the general trend shows that projects that appear to have adequate systems engineering effort are also the ones that experience lower percentages of cost overruns. So what we're going to be going through today is SEER-SYS, and SEER-SYS is a new parametric model that helps decision makers formulate and budget their systems engineering plans for a project. So what is SEER-SYS? SEER-SYS is the latest addition in the SEER suite of estimating tools. It's a standalone parametric cost model for systems engineering costs that's complementary to the SEER-H system level cost capability. It's equivalent to the SEI estimate that's generated by turning on the SLCs in SEER-H. It includes costs for acquisition and supply, technical management, system design, product realization, and technical evaluation. It's based on Galerath systems engineering research as well as COSISMO data, and it has been validated in the field with over 3 years of customer collaboration. And we'll get into the research background behind the model a little bit later in this presentation. So the model can estimate any from a system level of the systems down to box level systems costs. And it includes knowledge bases which help to preset parameters to commonly validated ranges. Okay, so this is a quick snapshot of what the tool looks like. You'll notice that it has a similar interface to other models in the SEER suite. So this might look a little bit familiar if you've used any of the other SEER tools before. So similar to the other models, you start with your create your work element window where you make your K-based selections. You have your parameter screen where you enter your system size characteristics, and you have the ability to adjust your cost driver ratings. And then you have your charts and reports so you can quickly see how the estimate's changing based off of your selections and inputs and what estimate is being generated by the model. Okay, so how does SEER-SYS generate an estimate? So SEER-SYS is a parametric model, so it takes your sizing and system description inputs that you enter in your parameter screen as drivers to generate estimates for effort, cost, and schedule. So SEER-SYS will generate an estimate for effort in terms of labor hours and generate a cost estimate based off of preloaded average industry labor rates. You also have the capability to load in your own company labor rates to generate the cost estimate as well. And then you also have the ability to capture uncertainty and vary your parameter inputs, and this captures risk, which can be viewed in one of the charts available in the model. So it's an example of that right here. So similar to the other SEER tools, we've used the data that we've collected to create knowledge bases that will preset your qualitative parameter inputs for you. You'll still need to enter your quantitative inputs yourself, since that's how the model sizes your system. So you'll need to enter your requirements or your operational scenarios and all of the sizing parameters yourself. But as far as the qualitative parameters go, we've used the data we've collected to create these knowledge bases. So there's 4 K-based categories within CRSYS. There's the environment platform category, the system level category, application, and acquisition. So the environment platform category describes the environment that the system will be built for or operating in. So some of the selections that we have available include air, manned or unmanned, commercial, ground, space manned and unmanned. And the system level category describes where in a system hierarchy that the system you're estimating falls in. So we have everything from system of systems down to the component level. So that's what we have here. So anywhere from an SOS down to like a tier 4 component level. The application describes the technical application of the system that you're estimating, and the acquisition describes whether the system is a completely new release or if it's a follow-on program that has heritage from a previous project. So let's say, for example, that you're working on a spacecraft and you want to estimate how much systems engineering effort should be budgeted for the thermal subsystem, which has heritage from a previous mission. So in that case, to set your qualitative parameters, you would select space unmanned for your environment platform, tier 1 major subsystem for your system level, space systems for your application, and follow-on program for your acquisition K-base. So by making these K-base selections, again, your qualitative parameters will be automatically preset with parameters consistent with the systems engineering data that we've reviewed for unmanned systems. And you'll still need to enter the quantitative parameters yourself. The other 2 K-base categories you'll see down here are the economic factors and other. We use industry average labor rates in the model, but you can load in your company's own set of labor rates by creating a K-base, and those would be loaded using the economic factors selection here. And the other category allows for you to create any other custom K-bases that you might want to make. Okay, so on this slide, we have a quick snapshot of the types of reports and charts that can be generated with CRSYS. So for example, we have a staffing by month graph, a costs by fiscal year report, an activity phasing report, and an hours by labor category graph. CRSYS can generate reports and charts for total costs, by month, by year, by phase, and by labor category. And similar to the other CR tools, again, calibration mode is also supported in CRSYS. If you have the data, you can enter actual effort or schedule and make calibration adjustments by phase. And if you have the data to support it too, you can also tune the model scaling factors. Okay, so along with parametric estimates for your systems engineering effort, CRSYS also supports non-parametric cost estimates, ensuring that no costs are left out of your estimate. So non-parametric estimates can be done for purchased items, fixed efforts, and duration-driven costs. So this would be particularly useful if there's a lot of additional training effort that may need to be captured that's above and beyond what's standard. So you could do that using like a duration-driven effort estimate. Or if there's software or material licensing costs that you need to include with your estimate, you can use purchase items and add that cost into your estimate. Okay, and CRSYS also allows users to build a cost catalog for standard labor hours and material costs, if that's something that comes up very often. Okay, and if there's a certain WBS that is standard to your organization, you can also save it in CRSYS as a scenario which is a pre-configured WBS pattern. So when you go to load a scenario, you can select which elements are applicable to the system you're currently estimating, and that WBS is what will be loaded. This is particularly useful for configuration control if you're working with a large group and you want all of your estimates to follow a consistent pattern. CRSys also allows you to create custom estimating relationships that tie together costs, hours, or quantities. Okay, so to summarize, CRSys includes all of your favorite SEER features like Monte Carlo and risk calculations, flexible export, server mode, knowledge bases, scenarios, the ability to make notes and attachments within your estimate, and an expressions editor. So now that we have some familiarity with how the model works, I'm going to go into details about the research background of the model. So CRSys came about because of the customer feedback we were receiving using the other tools. We saw that there was a demand for a standalone systems engineering model above and beyond what CRH and the RAP Vector approach is able to provide. So we saw that there was a demand to have the ability to create a more detailed and defensible systems engineering estimate, to be able to account for smaller issues that a RAP Vector approach doesn't capture. So these issues include things like personnel turnover or the benefits gained from a very highly detailed system engineering plan, utilization of SysML and any other system engineering tools. So RAP Vector's approaches did not reflect these details, but using CRSys, you can reflect these details. Another thing that we saw was that people wanted to be able to have a system engineering budget prior to estimating the hardware for their model. So instead of having to create your entire CRH model before you can wrap it and get your system engineering effort, this allows you to create a system engineering estimate prior to having any of that done. So the data behind the model, we leveraged the Casismo model, and then we also had additional collaboration with industry champions to develop our knowledge bases. So the data points within CRSys come from a huge range of industries. Majority of them are military, defense, and space, but we also have aircraft data in there, data systems, IT, scientific research, and telecommunications. So the original Casismo collaboration included data points from this group of companies in this table right here. And there were 30 data points in that original collaboration, or the original Casismo calibration. With CRSys, we've included additional data points that we've found from government, or that we've received from government contractors and government agencies. So we've included probably close to over 100 additional data points to the original Casismo collaboration. So the new data points that we received from contractors and government agencies were used to develop the K-bases that we have in CRSys right now. So using this additional data, CRSys is able to tune the estimates based off of system-level application, platform, and acquisition method, since we were able to see the nuances in the data points that we received. That wasn't something that we were able to see with the Casismo collaboration or calibration. The use of the K-bases provide industry default parameter settings that assist in building more defensible estimates, since the K-base settings you'll now have for your model are tuned to exactly the data points that fit with your scenario. So like the example we went through earlier, if you have that thermal subsystem for a spacecraft you're building, well, those parameters that were set with the K-bases are based off of space systems data points. And as new data is collected, our K-bases are continually being updated, and new K-bases are being developed as we see the demand and data for it. To ensure that all the data points collected are equivalent, include equivalent activities, we've used ANSI 632 as our standard WBS. And CRSIS addresses the first 4 phases of the systems engineering lifecycle that are defined by ISO 15288. So that's from conceptualization through transition to operations. It does not include the systems engineering effort associated with operating or maintaining the system, or the replacement or replace or dismantling of the system. So the 4 size drivers within CRSIS are the number of requirements, which the number of system interfaces, the number of business rules, and the number of operational scenarios. So those are your 4 quantitative parameters within CRSIS, and this is the one area in CRSIS that will require user input. Without this, there's no presets for the size drivers, and this is how you're going to describe the system you're estimating. So you're able to enter in your sizing inputs for easy, nominal, and difficult categories, and reuse of your systems engineering artifacts are also supported. So within each sizing input, so let's look at the system requirements here. You have your easy requirements, nominal requirements, and your difficult requirements, and then a range of least likely and most. And if you were to open this up right here, you would see that you can also you can go down another level and enter in the reuse behind those requirements. So if it's a new requirement, if it's a requirement that was designed from a previous system for reuse, if it's a modified requirement, or if it was deleted from a previous specification, or if it was adopted or managed. And here we have the size driver weights. So you'll see whether you enter in a system requirement as easy versus if you enter it in as difficult, there's a huge range in how that's going to affect your ultimate cost that comes out of the model. And within the 4 size drivers, you'll see the operational scenario has the biggest driver on what the effort estimate is out of the model. And then these are the factors behind each of the reuse category weights. Okay, so within CRSIS, we have 14 cost drivers. So these are your qualitative parameters, and these are what are preset by the knowledge bases. So there's 4 different categories that we have in CRSIS. So we have the problem and solution understanding. So this includes your requirements understanding, your architecture understanding, technology risk, and design decomposition complexity. We also have product and system complexity, which includes your complexity of your performance measures, the migration complexity from a legacy system, the documentation levels, how much documentation you have on the system, installation and platform diversity is the 4th one. We also have personnel and team capability drivers. So this includes your stakeholder and team cohesion, personnel and team capabilities, and personnel experience and continuity. And lastly, the last 3 qualitative parameters are your development and productivity aids, so your process capability, your multi-site coordination, and tool support. Okay, and again, all inputs are expressed as a range within CRSYS. So this is how the 14 qualitative cost drivers appear in the model. So this would be right under where you enter your sizing parameters. All right, and that is the end. So if there's any questions, I don't know, Kelly, you take it from here.